Alright, so in this example, what we're going to do is we're going to find an equation of the tangent line to the parabola whose equation is y equals x squared at the point 1, 1. So first of all, this word right here, tangent. Alright, a tangent line is a line that touches the parabola at one point. In this case, a parabola. There can be tangent lines of other types of graphs as well. But don't confuse this with the curve, the trigonometric curve of tangent. Alright, so they are a bit different. So, excuse me, to solve, sorry, hold on one second. Alright, I'm alright now. So, in order to solve this problem, what we need to do first is we need to take a look at a property of parabolas. So I'm going to go to our textbook for this. Alright, so there is a property called the reflective property. Alright, and what's really cool about this property is that we can find congruent angles in using this property. So here is what we have. So we have a parabola, alright, and we have a point on the parabola. So let's just pretend that that point is the point 1, 1, just like in our example. Alright, so if this point were 1, 1, and then this is the focus, what we could do to find the equation of this line right here, which is tangent to that point, right? It's tangent to the parabola. It means it's touching the parabola in exactly one point, and that point in this case is 1, 1. What's going to happen is the triangle, or the angle actually, that is formed by this line and then this, the actual tangent line, they create an angle right here. Alright, and then if you create an angle with the y-axis and the tangent line again, right, but the y-axis actually stops right here, which is where the tangent line crosses the y-axis, so that's the y-intercept. This angle right here forms an angle, and what's really interesting is that these two angles are actually congruent. Alright, so if you take a look, there is a triangle in here, right? And if you have two congruent angles, that means we have an isosceles triangle, which means that the sides across from those angles are also congruent. They are the same exact distance. So again, the focus to this point, that distance, is the same as the distance from the focus to the y-intercept. Alright, and so what we're going to do is we're going to use this property to solve for our example 3. Alright, so let's take a look. Feel free to pause the video if you need to write down this problem. I would encourage you to do this on graph paper. So I'm just going to go ahead and graph this out a bit. Alright, so I have the point 1, 1, so that's this point right here. Alright, and then I have a parabola. So I'm going to go ahead and draw this parabola. Ooh, that did not come out very good. That's kind of unfortunate because that's going to affect our tangent line a little bit. But if I draw a line that only touches this point in one place, right? Ooh, that's pretty terrible. But I have this y-intercept right here, and I'm just gonna make this up and say that the focus is somewhere here. All right. So it may not look it on this diagram, but according to the property, this distance right here from the focus to that point, and then this distance from the focus to the y-intercept are actually the same. So mine didn't come out because my parabola is definitely not perfect, and this tangent line, it may not actually be the correct tangent line. So what we're going to do to figure out the equation of this line, so remember we're looking for the equation of the straight, of this linear line, because that's the line that's tangent, that's the line that's touching the parabola. So what we need to do is we need to find 2 points. Now we know this point on the line, which is also the same point that the parabola shares, is 1, 1. Now if I could find this point, then I can figure out the slope, I have my y-intercept, and I could write an equation that looks like y equals mx plus b, right? That's the equation of something that's linear. So right now, all I know about this is that the x is 0, but I don't know what b, the y-intercept, is. So I'm going to have to figure that out, alright? So if I could know the coordinate of this focus point, then I could start doing some stuff. So let's go ahead and take a look at the equation for this parabola. Y equals x squared. Pretty standard. Right? Like that's the parent function, basically. It's the most basic form of a parabola. Well, if we take a look at the equations in standard form of a parabola, what we have is we would have, in this case, because the parabola is opening up, this would be, and I'm gonna switch the order of things just so that it kind of looks like what we have here, but we would have 4p y minus k is equal to x minus h squared, right? So we can tell here, and also by this equation, that the center hk are both 0. So we actually have 4p y minus 0 would just be y, and x minus 0 would just be x, right? So you can kind of see how things are starting to look like each other. So I basically have the y squared, I have the y's, but this right here looks a little bit different. But you have to remember that there is a coefficient here, so 1 and 4p have to be equal to each other. And so to figure out what p is, which remember is the distance from the vertex to the focus, I can just set up an equation where I set both of these two things equal to each other, because they are substitutes of each other. This is just the simplified version of whatever was here. So I can just divide both sides by 4. I'm just working backwards. And I can see that p was 1/4. So this distance between the vertex and the focus is 1/4. And so the reason that that's important is because now I know the coordinate here. The coordinate of the focus, just going to make a line there, is 0, 1/4. Alright. Okay, so now what we can do is we can figure out this distance, because then I can copy that distance here, and I can figure out how far away this point is, and I can figure out what b is going to equal. Alright, so we can just use the distance formula. So what we're going to do is we're going to do distance equals the square root, right? And then I'm just going to do y2 minus y1. Oops, those actually should be sub notations. Squared plus x2 minus x1 squared. Alright, so my y is 1 minus 1/4 squared, and then plus, and then my x's, it actually doesn't matter if you do subtract your x's first or your y's first, because you're just adding, so either way, you've actually probably seen this as x2 minus x1, but again, it doesn't matter because this is commutative. And then we're going to subtract the y's, so 1 minus 0 squared. Alright, so we're doing some math here. I'm going to make 1 4 over 4. So 1 minus 1/4, or 4 over 4 minus 1/4 is 3/4. Alright, 1 minus 0 is 1. Alright, so let's keep doing some math here. 3/4 squared is 9 over 16. And 1 squared is 1, but let's go ahead, because we have to add these, make that a 16 over 16. Alright, so if we add these together, we have 25 over 16. The square root of that is going to be 5 over 4. Now you could have plus or a minus, but we're going to go ahead and just use that as a distance, so we know we're just 5/4 units away. Okay, so what this means is that the distance from here to here is 5/4 units. So the distance from here to here is also going to be 5/4 of a unit. Alright, so if I take this y value, which is 1/4, and I go down 5/4, because that's the distance. Alright, 1 minus 5 is -4. all over 4. So that equals -1. That means that this coordinate is 0, -1. I actually was kind of close. Look at that. Alright, so we have this point, which was given to us. We found this point. Alright, so what we want to do now is we want to find the slope. Okay, so now we're working towards making that equation. Alright, so we have y equals, my slope is going to be y2 minus y1 over x2 minus x1. So y2 is 1 minus y1, which is -1, all over my x2 minus my x1. So this becomes plus plus, so I have 2 over 1, which is 2. So my slope, m, is 2, and b, I have right here, this is my y-intercept, so b is -1. Y equals 2x minus 1. Alright, so there are lots of applications for finding the equation of a tangent line to a parabola. And this is actually something that you do a lot in calculus, although in calculus you do that by finding derivatives, which is basically finding the slope of a curve at a specific point. And the reason that we do that is because imagine a real life scenario where you have data that's being graphed, right? And let's say that that graph looks, in real life, graphs don't really look linear, right? Things don't exactly change the same amount all the time. I mean, there are certain things that might, but more realistically, things don't. Let's say you had a graph that looked like this, right? If you want to find the slope of this is a curve, it's not a straight line. So let's say you wanted to find out how fast are things changing at this point, right? You might think maybe each one of these tick marks is an hour, right? Is a certain hour during the day. Maybe this is temperature or something like that. Or maybe it's a month. Maybe you're tracking, I don't know, something crazy like the rapid growth of a virus throughout the world during the pandemic. Crazy. But you can basically make projections. You can figure out estimates of how quickly things will change, whether it's an increase or a decrease at specific points in time is really what things like this are used for. And so when you can find that tangent line and the equation of it, you can figure out things like that. Now this is like a whole world of math, and there's much more to this than what we've just done, but this is just a very basic example. But this is something that I really want you guys to know well and to start understanding, because it's definitely something you'll see in calculus, but it's also important to understand how things actually work in real life, and that things are not linear and perfect like what we see in our textbook all the time. So this is just a little bit of an introduction to that.